professor at Department of Earth Sciences, Indian Institute of Technology, Kanpur. That's all written over there, yeah. So this is my group members. We have a postdoc, several PhDs, and master's students, and the funding organizations who have thankfully given me some money to carry on the research. The the idea behind developing this lecture was to discuss with you the the causes of landslides. When I say cause, I mean both. What are the real controls on the landslide, and what triggers landslide? Usually in news or popular media, we are exposed to the triggers of landslide. The one of the most important trigger of landslide is rainfall. But there are controls on landslide, controls that we can use or as a tool to mitigate landslides. All right. So this would be the structure that we'll this will be the structure that we'll follow. Small introduction, why landslides are important, a small history of Indian landslides, uh, their geographical distribution in India, components and classification of landslide, and then kinematic analysis. So we all know, especially after some of the most tragic events, that landslides are movement of earth material. Movement of earth material specifically on associated or situated on the slopes. Now, why do landslides happen? Or why study landslides? Because they cause a lot of damage to humans as well as properties, yeah, and they usually affect hilly terrains. Main triggers of landslides are rainfall, earthquake, and unscientific human activity. The last is what we are going to talk about today. Uh, does anybody know or can guess why do we have so many landslides in Himalaya? Why not are there as many landslides, for example, in Rocky Mountains or in Andes? There are, of course, but why not so many? One reason is that we do not get a lot of information from there, so it's filtered, it's international news, but why not so many? Have you ever thought about this? Yeah, Himalayan and young mountains, true. What does that imply? What does that imply to active tectonics? Yes. Is there anything else? The lithology of Himalaya is unfortunately very well suited to landslides. The rocks are highly deformed, and a lot of rocks have very fine grained structure, which makes slippage very easy. Plus, they have a high porosity and permeability, which allows seepage of water. Yeah. So Himalaya is especially suitable for landslides. It's not just the bad construction or bad planning, but it's also geology that controls, and because of which we have so many landslides in Himalaya. Going back in memory, as far as the records go, some of the oldest or biggest landslides were in 1948, where 500 people died, unfortunately, in 68, in West Bengal, Darjeeling, in 1998. Then in 2000, this is now recent memory, and some of us may have heard about these, yeah. But maybe most of us know about the 2013 Kedarnath landslide, and Ankit also talked about this, yeah. 40 people died over there, but the devastation was eye-watering. Yeah. Uh, then we have Mandi and Himachal landslide. The latest are not here. These are the states which are most affected by landslides, and you see that the darkest green are in the Himalayan region. Yeah, Lesser Himalaya, and then but we also have landslides in the Ghats. So in the western and the eastern Ghats, which is the margin of the peninsula India, if I use so this is the western Ghat and this is the eastern Ghat. Yeah, we also have landslides there. There we usually have basalts, which are a bit more stable than Himalayan rocks, but unscientific practices lead to landslides. Very shortly, I would like to give you an introduction on the components. Is it clear till now? Yeah, any question? If there is a question, please stop and ask. These are the components of landslide. So we have the the uh, the original ground surface here given in teal color. Yeah. So for landslide, we need a slope. If there is no slope, there will be no landslide. Yeah. There should be, and the steeper the slope, the more chance there is for landslides. Unfortunately, I was talking to a friend in IT Roper, and he said that The NHAI doesn't have a special code for making roads in Himalaya. So they are using the same codes, same standard operating procedures that they use in plains for making roads in Himalaya. Now you can understand making a road in an alluvium plain in Uttar Pradesh, for example, or Bihar is completely different, where there is no mountains. Yeah, we do not need to worry about the slopes near the road cuts. However, in Himalaya, they do not have a different standard operating procedure. So they design or they plan that this is the shortest route to make a road, and then they cut. They use JCB and the dynamites and the JCB to blast away everything. Yeah, and if you see, there are a lot of videos also on YouTube where it is said by slightly proud that they are Himalayas have some of the most dangerous roads, and you will see that the roads are cut like a half tunnel, so the rocks are hanging on. Of course, it's funny, it's very funny and very interesting until it falls on somebody. Yeah, so these kind of practices are because there is no standard operating procedure for to cut in India to cut roads in hilly terrains. And then for those who have already studied a bit of geology know that Himalaya itself is made up of different type of rocks. So for example, the amount of landslides in higher Himalaya, say which are crystalline rocks, hard rocks, is much less. You will not hear so many landslides in higher Himalaya, whereas in lesser Himalaya, which is much highly populated, regions near Rishikesh and Devprayag, yeah, which is very near. So this entire belt, this is highly populated, a lot of road network, less vegetation, but also the rocks are weaker there. But we are using the same methods to make roads and dig canals, etc., which we use in the plains. So we do not have a standard operating procedure, which boils down to unscientific practices. Anyways, away from the tragedy and coming to the science. So we have the main scarp, this is the first fracture where the material starts to move, and then this material pushes the one which is below it, and thus we have a cascading effect of landslides. So it is an initial movement, trigger movement, which starts to push other material, and then we have a big landslide. So we have the main body of landslide over here, then we have a toe of the landslide, and then you also see that we have some transfer cracks. As the landslide moves downwards, the volume increases, the space which it has to occupy increases, and thus there are fractures developing in these landslides. And then at the end we have the toe of the landslides. Now, landslides are landslides based on the geometry or based on the mechanism are classified into several parts. There are falls, yeah, which is for example, which I was discussing. If there is this C kind of road cut, then this material will fall down, and this is called a fall, a landslide. Yeah, absolutely catastrophic for a vehicle which is going below it. Then we also have topples. Topples is like a bookshelf where the book topples down. This is also very common. We also have rock slides, yeah, which is shown over here. So the entire rocks slide down. And then we have lateral splits and flows. Flows are some of the quite common landslides in Lesser Himalaya in this region of Rishikesh and Devprayag, in this entire belt. Yeah. When I say Lesser Himalaya, I mean where the Himalaya starts. Yeah. So if you consider Roorkee, then Lesser Himalaya starts somewhere, say between Rishikesh, between Haridwar and Rishikesh, somewhere where you see the first mountains. Okay. And these are very fragile rocks. They are old rocks, but they have been deformed and uplifted, so they are very fragile. And now, because we are only going to talk about the structural controls, we will only talk about rock falls and topples. We will not in this lecture we will not talk about flows, because flows usually is unconsolidated material. They are not rocks; they are mostly mud. But as you see, or by this discussion, I guess you are already trying to appreciate that deforestation, etc., or unplanned growth is one of the biggest reasons for landslides and the cascading effects. So we'll focus on these two today. So I have some examples of landslides here. This is a rock slope failure, and if you see very carefully, there is a discontinuity over here. Yeah, can you see this almost flat surface, or shall I zoom in further? Yeah, can you see this almost flat surface? Yeah, this is a failure, and then there is an almost flat surface over here, so they're forming a kind of V. Yeah, and this is a wedge type rock failure. It's a small scale, but this happens on a larger scale as well. Then we have this another very classical example from Canada for a rock slope failure. This is very common in India, yeah, where this and the entire unconsolidated material flows down because the slope is very steep. So at the moment in this lecture, we are talking in very qualitative terms. We say that the slope is very steep, but I hope that by the end of this lecture, we will be able to quantify how steep the slope is, which is causing the landslides. Okay. So for now, remember that the slope is very steep, and this flat surfaces are also steep, and they are intersecting, yeah, like this, and thus we have a landslide. Another rock slope failure, you see this entire material is falling down, but in also over here also you may appreciate, or you would appreciate, that there are these flat surfaces. If you consider this bow wire, then almost parallel to the bow wire we have these flat surfaces running like this. Yeah, so there is something between these surfaces and slope, some kind of interplay between these surfaces and slope, which causes landslides. These surfaces are structural surfaces. We'll talk about them. Yeah, first a few more examples. Again over here I will zoom in. So you see two, where is my cursor? So you see there are two surfaces. You can't see my cursor. There are again these two flat surfaces, one over here and one over here. They are intersecting, and thus we have a landslide here. These are all small landslides, not catastrophic, but these are good examples, because if they are large ones, they usually break everything. When they move, they break all the rocks, and then we do not get this, say, incipient phase, the initial. And this, now you can already guess what kind of landslide is this. So that block where this dude is standing, this fell down from here. So can you guess what kind of landslide this is? We talked about it. What is common in all of these cases? What was common? We have a slope and we have structural discontinuities. Yeah, and the failure always happens along the discontinuities. Yeah? In all of these, so we have intersecting surfaces, or we have one surface in the bow wire photograph, and then the failure, the initiation of the landslide always happens with a failure. There is a fracture which causes the initiation of the landslide. It doesn't matter if we are talking about rocks or mud. Even in mud, there will be a crack. There will always be a fissure, an opening, a fracture that will initiate the landslide. Okay, and there are ways to say understand or to predict if that particular area or that particular fracture will cause landslide or not. That we will do in the coming part. So we need a discontinuity along which the failure happens. The second important thing is the orientation of the discontinuity with respect to the slope. This is very important. So when we do these, I'm teaching structural geology in Kanpur, we do this kind of exercise where I give examples to the students and ask them if there will be a landslide or not. So a very basic criteria that was used earlier is if the rocks are slanting like this. Yeah, when you travel in Himalaya, you will see the rocks are slanting like this. So if you cut a road on this side, there will be a landslide. If you cut a road on this side, there will be no landslide, irrespective of the slope. Yeah? So if you cut a road on this side, there will never be a landslide. So this is a very basic qualitative method we can use to stop landslides. But this only works in roads. This doesn't work with rivers, because rivers are a V-shaped valley. Yeah, so this only works with roads. If you have rocks like this, for example, and there is a dam or there is a river channel like this, then you have both rocks sloping like this and sloping like this. They will have a landslide. This will not. I'll show you better figures than my hands so that it's easier. So now we can use kinematic analysis to understand the potential of the failure. Yeah, and this potential of the failure depends on the discontinuity orientation. On the orientation, which means how the discontinuity, how the structural discontinuity is oriented in space with respect to the slope. There are only two things that we need to worry about when we are talking about landslides. Don't fall asleep. Where were we? We were talking about the structural discontinuities and the slope. Yeah. So there are three parameters that one needs to know for mitigating landslides. You need to know the orientation of the slope, which is very easy. Yeah. You know the slope orientation. You need to know the orientation of the structural discontinuity. That we will teach you. This is, and the entire lecture is about that. The entire 2.5 hours of your life would be dedicated on this. And the third is the angle of internal friction. So for most of the rocks, we have standard charts which give us the angle of internal friction. And angle of internal friction can be assumed in a way, for example, if you see a pile of rubble, yeah? So gitti, morang, balu, three different materials. If they are piled on, all of them will have a different angle. Yeah, one would be steeper, stable in a more steeper setting. The other would be stable in a more gentle setting. I hope you understand these three. Great. Yeah, and then two different sides of sand. That is caused by the angle of internal friction. So higher the angle of internal friction, the steeper the material can be stacked upon. Okay, so a Lego block, if Lego the game, yeah, it mathematically has an infinite angle of friction, because if you stack them on top of it, they will never fall down, they will never slip. So of course practically it's not, but by mathematics they have an infinite angle of friction, they'll never fall down. Similarly, rough cubes will also have a very high angle of internal friction, they will never slip until there is an external force. Anyways, coming back to our discontinuities, what type of discontinuities they are. So we have already talked about rocks. Rocks have surfaces. Yeah, if they are rocks in Himalaya are sedimentary rocks, most of them formed in a Tethyan Ocean. I hope a lot of you know about this. So before India collided with Eurasia 70 million years ago, so the collision started 65 million years ago, 60 million years ago, there was an ocean called the Tethyan Ocean. And the rocks were deposits. So the sediment was deposited in these oceans, and then because of the overburden pressure, they became rock. And when India hit Eurasia, the material was abducted, and this is how we have formation of Himalaya. I have a very simple example. So we don't use handkerchiefs anymore, so that would have been a great example. But if you have a piece of paper like this, assume that these are the thick sediments, yeah, and they're lying on the crust. Now we have Eurasia over here, we have India over here, and when we press them together, we have Himalaya forming. It's just simply like that, as simple as that. Because the material couldn't go down, there is mantle, it came up. Okay, so it was pressed on the either sides, on one side by Eurasia, on the other side by India, and below we have mantle, so the Himalaya came up. So most of the rocks, coming back to the story, are sedimentary rocks, and the sedimentary rocks form layers. These layers are called beds. So geologists know this, yeah. And these are this should have been animated, but yeah, sorry. So they are beds. Similarly, if you see deformed rocks, they also have layering, and they are called foliations. And then we have shear zones and fault plains, which are fracture surfaces of different kind. So in summary, there are 4 kinds of discontinuities. All 4 of them are planar. I hope you understand what planar means, which means they are 3D surfaces and they are mostly flat. Yeah? Not very curved. Of course, it's nature, so nothing is perfect. They are curved, but they are more or less flat. Is there any question till now? We are almost at the end of the lecture. Okay, let me finish and then I'll ask. Now, to orient a plane, let's consider this to be a plane. Yeah? To orient a plane in space, we have all studied it in geometry. What do we need for a plane? There are several ways to orient a plane. One of the ways that we get 2 points on that plane, yeah, in space. For the points, we need coordinate system. Yeah? So if we have a XYZ coordinate system like this, and we want to orient a plane, one way is to get 2 points on the plane and we can orient it. The other way is to get the X, Y, and Z intercepts. Yeah? If we have the intercepts on the X, Y, and Z axis, we can orient a plane. One of the easiest way to orient the plane is if we know its slope, yeah, which in geology is called dip. This is a very important word which you should remember. So this is a horizontal plane. If it is dipping, if we know this amount, yeah, the amount of it's slanting or sloping from horizontal, and we know the direction in which it is dipping, north, east, west, south, etc., then we can orient a plane. Okay, please remember this. And this is how we orient a plane. So this is a plane here. It is sloping in this direction. Yeah, 2 is the arrow which marks the direction of slope. So 4, the angle number 4 is the angle which is it is making. This is the amount of dip. Yeah, and this direction of 2 would give us the direction of slope. Okay, so for example, if this is north and a plane is slanting like this, then its orientation would be say 45 degrees towards north. This is horizontal, it is dipping 45 degrees towards north. Is that clear? So if that is north, this is east, I hope. So this is dipping 45 degrees towards east. If it is less, then maybe 10 degrees towards east. Is this clear? I know for you, yes, because I taught you twice. But for others, because the entire next 1.5 hours is about finding this in from drone data. Is that all right? Is that clear to everyone? Good. So I forgot to say, and Bhagirathi told me to say that before. Have you already downloaded the things that were emailed to you? Yeah, if not, then please do it. So we have the strike dip, yeah. And then if you have not done this, then please download. You can ask your colleague to send you the email, because it takes time. It is 2 GB of data. Yeah, so it takes time. And also there are softwares in it. Yeah, so please download them. Now we come to the important part, which is kinematic analysis. Don't worry, we already did the qualitative kinematic analysis where we decided that the slope should be less of the surface and the bed should be dipping in the opposite direction. Yeah, so now since we know, chale kar lijiye, do it. And then you look here. So I'll give you a couple of minutes. Once you click, and then we can talk again. Click on the link and it will download on its own, hopefully. And hopefully it will run on your laptops. Otherwise we'll teach you how it's done. Anyways, okay. So kinematic analysis sounds a very fancy word. It is not. We have already done that actually in this lecture. We talked about 2 features. The first is that if it is not sloping so much, then there will not be so much landslides. Yeah. So the first factor of kinematic analysis is the slope of the surface should be less. If there's no slope, then there's no landslide. The second is, of course, now we know the dip of the beds or the structural discontinuities, in a very fancy word. If the structural discontinuities are horizontal, there will be no landslides. If they are dipping more, there will be landslides. The last, which we also already discussed qualitatively, is the play between the slope and the structural discontinuity. Can you hear me? I guess so. So for example, this is a mountain. Very simple image. And we have fractures or beds oriented like this. A very, very trivial cartoon. Yeah? This is, pardon my bad drawing, but I wanted to do it in the class rather than making a, say this is east. Yeah, I hope I can draw it. Okay, say this is east. Now we know now that the beds are dipping towards east. Is that all right? Please, please, please. Yeah, you will get more time to look at your computer, to work on your computer. Of course, you will have a lot of time to look on your computer, but yeah, so the beds are dipping towards east. Now we need to know 2 things. In angle of internal friction, you will get from geotechnicians or from us. We need to know the angle of the slope. So we change the color of the pen somehow to green. Yeah, and this angle is the angle of the slope, right? Clear? Okay. Where is the angle of the structural discontinuity? That would be, so if the green line is horizontal, more or less, yeah, then this is the angle of the structural discontinuity. These are the two things we need, the slope and the structural discontinuity. What we have been doing till now in India is, well, we haven't been considering neither, and thus we have those kind of tunnel, half tunnel roads. But this is both we need to worry about. Let's have a couple of examples of landslides. Okay, so this is a planar failure. This means there is a plane on which the landslide is failing. Yeah. So this happens where the discontinuity intersects the slope. So if the structural discontinuity is intersecting the slope, we'll have a planar landslide. However, if we have two structural discontinuities which intersect each other, make a V-shaped thing, for example, the gray zone here, and then they intersect the slope, we will have a wedge type landslide. We may also have topple, where the structural discontinuities are steeply dipping. Here you see. So these are the structural discontinuities and they are dipping steeply. So if we try to measure the angle from the horizontal, they are dipping by about, kitna dip kar rahe hain? How much are they dipping? Can you guess? Not these fellows. So you know this angle is the dip angle now, yeah, between the structural discontinuity and the horizontal. How much that would be? 80 degrees, 75 degrees, something like that. It doesn't matter, but it's steep. So if it is dipping steeply and the slope is dip also like this, then we'll have topple. This means they will fail like bookshelves. And the last one is of course circular, which happens in soils and waste, and which is highly fractured and with a lot of plasticity, and there are very few structural controls over here. So thus we will talk about the planar, wedge and topple landslides in the further lectures. Here are some more examples of a planar landslide. You see, they are all planar surfaces here. And since you already know, these are all the bedding or fracture surfaces, and the landslide happens in this direction. This is another example, same that we have already used. Yeah, so the landslide is happening here. You see the rubble here. Now the criterias. Now this is where you have to pay attention. A planar landslide will happen when the discontinuity dips in the same direction as the slope. Okay? So what we talked about initially, you remember this figure which I was trying to make? I'll draw it again. So if this is the mountain face, this is our structural discontinuity. Now considering this rule, yeah, and say this is left. Is it clear? Left? Yeah, okay. It's better than, and this is right. And we say that the first rule is that the landslide will happen on faces which has the same direction as slope. Will it happen on the left or the right? Left, yeah? So now we know if we suppose get a chance to and we have an opportunity to make a road, we should make a road section on the right side, not on the left side. Fine? There will be very less chance of having a landslide on the right. Then the second is that discontinuity should dip at a gentler angle. So you see it is dipping at a gentler angle. Let's see what happens if it is dipping at a steeper angle. So I'll make another. This is our mountain face and it is dipping like this. Yeah. So our intuition tells us that there will be no landslide over here. And we already know it by intuition. These are just rules that have been made based on intuition and laboratory studies. We know that there will be no landslide over here. Okay. Then the third is that the discontinuity should dip. The angle of the discontinuity should be greater than the friction angle. Okay. So these are the three rules which we need to know for both of the landslides, planar as well as wedge. There are these three rules, that the discontinuity should be in the same direction as the slope, the discontinuity should have a lesser dip than the slope, and but the discontinuity should have a higher angle than the angle of internal friction. For the wedge, instead of the discontinuity, we use the intersection of the wedge. So this is a very nice photograph of a wedge landslide. You have a plane over here. This is a plane. This is a plane. They intersect, and then there is a landslide. Another wedge failure over here. Yeah? The criteria for wedge flares are also the same, but here instead of the discontinuities we consider the line. So if this is the discontinuity, the line made by the intersection of the two discontinuities. So the line made by the intersection of the discontinuity should be dipping in the same direction as the slope. The dip of or the plunge should be less than that of the slope, but the plunge should be higher than the angle of the internal friction. Now we come to the last one, topple. Topple is a slightly more complex story, but not too much, just slightly. Uh, don't worry about the figure. We have already talked about all of this. So phi j over here is the angle of internal friction. Yeah. Sigma over here is the angle of dip, and alpha is the angle of the slope. So we have already talked about the three variables. And according to Goodman, they will be topple if 90 minus the dip plus the angle of internal friction is less than the slope. So these are very three simple rules by which we can try to mitigate landslides. It's very simple, and believe me, determining these angles, except the angle of internal friction, we need to do laboratory testing for that. Determining the angle of slope and the angle of discontinuity is a very trivial job. A trained structural geologist needs a couple of seconds, not couple, maybe 5 seconds to do it. But you have to go in the field. Thank you. Well,